we introduce two damaging points. We instrument this bridge along its length, and these are natural frequencies we get from particular modal analysis. So due to this damage and to these two different points, we see changes in the natural frequencies. But this is what we want to detect through our algorithm. So we assume a sine sweep excitation, so we have broadband excitation in the frequency domain, but we have highly non-stationary signals in the time domain, and we want to see how different wavelet bases are doing. So in terms of sparsity, okay, so in terms of sparsity, what do we see? We see that the harmonic wavelet base is the most sparse compared to other wavelet bases, and this reflects on the level that we can detect the location of the damage. Remember, we have these 2 points that they have been, our bridge has been damaged. Okay, so we can see these 2 peaks are much higher than changes in the wavelet entropy that we see from other points. And this is not so apparent if we use different wavelet bases. So we have a sparsifying, essentially, basis function, and now through the compressive sensing, we can go on and define our sparsifying matrix together with our random sampling matrix. So we have a partial harmonic wavelet basis, we simply use Cosamp algorithm for sparse reconstruction, and this is the map that we are getting with a compression ratio of 30%. That's 70% lower than the Nyquist frequency compared to what we have with the free frequency. So we see a very similar picture, and this is of course because of the fact that our basis has been properly selected to really give good results. So this is, as we go into more and more compression, up to 90% below Nyquist, we still can detect the damage. And of course this means, as we will see later on, huge savings in terms of energy spent at the sensor. But of course, all this hard work was possible because we were able to find a sparsifying basis. But this requires a lot of work. So what if we don't have to? What if we try to now look into ways that we go beyond sparsity and we don't have to look into any particular basis function? So to do that, we have been looking into what is called the power power spectrum blind sampling technique, where we do again sub-Nyquist sampling, but multi-cassette sampling. Okay, so it's deterministic, non-uniform in time, and we go and we try to do power spectrum estimation from this sample, sub-Nyquist sample data, and then through standard frequency domain techniques that we have for system identification, we can go on and find mode shapes without. The good thing about this method is that it doesn't have to obey to any particular sparsity conditions. So all we have to solve is a system of linear equation, no sparsity constraints, and this also means essentially that noise, theoretically at least, does not affect our technique here. So what is multi-cassette sampling? Where if this is the Nyquist grid of samples, we are dividing our time domain, you can think of dividing our time domain discrete time signal into blocks and length, and within each block we are getting particular locations that are defined through the sampling matrix. We are getting m much smaller than n number of samples, but these samples must have the same position with each and every block. So we're getting the red samples from each block at index 0, the blue samples at index 2, the green samples at index 5, so on and so forth. And in this particular application, we're getting 3 out of 8 samples within each block, so this means overall we have a compression ratio of 37.5%. So we are about 65% lower than the Nyquist sampling. Now, this is a depiction of how multi-cassette sampling would look like if we are to, let's say, think of it in terms of a filtering operation. We have our signal entering n different channels and then downsampled by n, and after being convolved with this sampling sequence. So 1 when we want to choose a sample, 0 when we let it go. Of course, you may tell me, okay, is this doable? There's some recent work on multi-cassette samplers that can do multi-cassette sampling without essentially have so many interleaved channels. So our contribution is that what happens in the case where we have d-identical samplers, or d-sensors, that they look like this, and what we find is that if we take the cross correlations of every channel with every other channel of each and every sensor, okay, so we form this output cross correlation matrix, then we can do, estimate relatively easily the power spectral density matrix, okay, through this pseudo-inverse. And the good thing about this is that this sampling R matrix is very sparse, and it's efficient to do that. So after having this power spectral density matrix, then we can apply what is called the frequency domain decomposition. It's essentially application of the singular value decomposition to this matrix, and we can retrieve mode shapes and natural frequencies. So let's look at some examples. So we are monitoring here a wind turbine that has been used to produce renewable energy. The interesting thing about these structures is that because of this rotation of the wind blade, we are usually getting non-stationary measurements, and this is not this violates the assumption of stationarity that our approach is obeying to. But if we look at, if we window our data and we apply a very well-known statistical test about stationarity, we see that we do have stationarity under some good confidence, within some good confidence levels. So we are comfortable with dealing with these kinds of data. And now these are spectral, how good we do in terms of spectral estimation as we go to higher and higher compression ratio, down to almost 90% lower than the Nyquist, using, of course, different sampling patterns. These sampling patterns are coming up by solving a quite computational intensive optimization problem, but this needs to be solved once, okay, when you, at the stage where you design your sensor. And then number of channels and downsampling. So as we go to higher and higher compression, we see that in the linear scale we do very well. Of course, we are losing information if we plot this in decibel in a logarithmic scale, but the information that we want in structural health monitoring lies in these first few peaks. So we are doing very well, for example, in estimating natural frequencies. These are the errors that we see in estimating natural frequencies as we go to more and more heavier and heavier compression. Okay, so we have very small errors in the main natural frequencies that we care about. So let's look a little another application on damage detection. We are using a particular now physics-based damage index. So if we have a beam, for example, and at a particular location we have some sort of damage going through some reduction of the flexural rigidity, this means that our mode shapes will change a little bit, and the question is whether can we track this change. So again, we will be using our technique to come up to find the mode shapes, and then from those mode shapes we try to detect damage. So our test specimen here is a beam that we introduce heavier and heavier damage at midspan. So that's the location, it's the middle of our steel beam here. So these are the mode shapes that we are getting from Nyquist sampling and from sub-Nyquist, 70% fewer measurements. So we are doing a good job even if we have a signal-to-noise ratio of 10 decibels. This is the noiseless case, this is the extreme noise case, let's say. And these are damage detection results for noiseless case,